Okay, so it's me from Institute of Physics. My collaborators, I would like to mainly mention Jan Racek, who is behind this research. And well, I really appreciate the morning talks about frontiers in fatigue, which was kind of, and so particularly this comparison between the rubber and steel, how we are in between. But in reality, we have here this phase transformation, which should be regarded as a reversible process. In fact, it's not, but theoretically, Martin's transformation is reversible, so we should think about it like a reversible process. And in ideal case, this could be repeated for 200 million times. And it seems to be it's not possible with wires, but recently it was published with thin films. If you have a slightly different composition with titanium rich, and it looks like they measured 10 to 7 cycles without any change of functional behavior and without any fracture. But if you put the same figure, which looks very nice here, if you put it into the same frame, you see it's below 1%, so in fact it's kind of limited. But still there is a chance and there is where to go, and probably we can have.
The laser pointer is there if you want.
I just don't know how to use it properly. And so there is a probably chance to reach such kind of high performance nitinol, but there are difficulties. So maybe I can go again. I can think about what kind of difficulties we have. So one of them is this compatibility on the lattice level. And these people in science, they claim actually that if you have precipitates which are strain compatible with austenite and martensite, they strengthen the batteries but don't prevent the phase transformation. You can reach such kind of stable behavior. This is basically the idea which is in this Kulba's paper, which means that if this is solved, probably it would work. But still, in a real wires with grains, you will have these kind of things and residual stresses, so we need to understand these things as well. Wire intention will not deform homogeneously, but will deform in this way, and here there is a strain change up to 6 or 7 even more %, so we need to understand this localized behavior because it's very difficult to get rid of that. And finally we have here the inclusions, and the cracks always start at the inclusions, so at first if we want to do something we have to get rid of the inclusions. But even if all this is solved, I would like to come here with another frontier, maybe, which we have to go around, and this is surface finish. Probably there was no time for surface finish, otherwise it would be between the frontiers as well. So if nitinol deforms in liquid, on the surface there is oxide, and this oxide is absolutely necessary because without oxide it will corrode immediately. So we need to have the oxide on the surface. The question is how this oxide actually looks like. So to test the corrosion of the fight against environment, one can perform potentiodynamic test, and this is on the oxide which is just in strike position, but if you bend the wire, you break the oxide, you get a little bit different behavior, but it's not disaster. It still performs quite well. And we put the wire on the spring and put it for half a year into very aggressive fluids, and even after that the strength didn't change. So actually, if it's static, the oxide works quite well and can protect the wire. The problem starts when it's dynamic. When you submerge the wire into the fluid and start to cycle it, immediately, not only that the oxide will crack, but it will crack in millions of such tiny nanometer size crack, which upon cyclic loading then periodically open, close, and you are like in a house where you want to be against the cold, but the doors are open and close every 10 seconds, which is not probably so easy. So let's think a little bit more about this mode of periodically opening, closing cracks, because now you are with the electrochemistry, and if you open the crack, you let the fluid to be in the contact with the bar metal, and immediately these chemical reactions will start. And so here, this is like this figure, and we think that this was already published in the literature. Actually, this is what damages the material, but it was not clear. It was not clear how. And to know how, you have to have some experimental method which sees these processes at the level of oxide cracks, which could be like oxide could be in 10 nanometer. And this method is electrochemistry. If you cycle the wire with machine and put it into the electrolytical cell and you measure the open circuit potential, you get the information on what's happening on the surface of the material. And so if you continuously record this potential, which is the result of the chemical reactions, you see some drop at the beginning and then periodically cycling until the fracture. I would like to little bit to explain about what is behind on this. So this is a single experiment where it's time, this is stress, this is strain here, and this is the OCP. So we just pull a little bit and straining here, and then the strain is constant. This is the stress response, this is the OCP response. So once you break it, the OCP goes down and then quickly increases. The problem is with the data recording, if we can record faster, it will probably go deeper, something like this. So we believe that here the oxide is broken, it comes to the contact with the material, then this is reflected by the decrease of the OCP, then this reduction will start here, which however produces the oxide, like an oxide gel, and it also produces the hydrogen here. So inside these cracks, you have the hydrogen production. If you do it repeatedly in one cycle, this is how the response look like. So this is superelastic curve, and this is the response of the OCP. Fracture, and then some kind of recovery. I already shown this figure, and so I would like to emphasize that the harm is not from the fracturing the oxide. The harm is from periodically opening, closing, and the hydrogen production inside. And these electrochemical methods can follow what's happening on the surface. Okay, now, yeah, this is on the spring, because we did also work on spring. With spring, you can have kind of gradually increasing. You don't have these shear bands. And this is the OCP response upon cycling. So again, you have the drop here, and then periodic cycling. So here, there is some kind of repair of the surface in corrosion terms, here stable behavior, and when finally the cracks start to grow, 1,000 cycles before, you see actually this decrease, which is the evidence of suddenly selected few fast growing cracks. While you don't see anything on the mechanical response, anything on the electrical response, because it's just really localized to the surface. If you do the same but stop in some moment, immediately the chemistry works and the original level of OCP will be recovered. But once you start to cycle, you come down. So evidently this is the evidence that in static and in dynamic regime, the oxide works in completely different way. It's a very good statistic. There is several springs with one type of oxide, with different type of oxide, the difference in about 1,000 cycles. Finally, all these things break because of inclusions, but the statistic is still pretty good, and so one can see the effect of the surface on the fatigue performance, and my colleague Lukáš Kadeřávek will talk more in detail about this later. But I would like to, I go back to wires here. This is somehow related to the pre-strain effect. So actually, well, before I spoke about full superelastic cycles, but now I will speak only about the elastic. So elastic with small pre-strain, elastic here. And this is in logarithmic scale. So you see, by far the best performance is in the martensitic state. But you have large stresses and large pre-strains, see about 20 times higher number of cycles still failure under these conditions. So why is that? But this is maybe the summary. This is the performance in air, this is in fluid. Always in fluid worse than in the air. But what should be compared here is in the elasticity, in the transformation regime, in the martensitic regime. Here, by far, the largest. This is some kind of scenario I would like to explain why it happens. When you are in elastic regime, it takes many cycles before the cracks make it down to the matrix. If you are in superelastic regime, the cracks make it here, and you have this problem with the hydrogen production and the opening, closing cracks all the time. If you are in martensitic, the cracks are all the way open because the pre-strain is about 8%. So you have this gel, the oxide, which is created by the chemical reaction. It's open, close, but there are not really many problems with the matrix. So we believe this is the explanation, but there could be other explanation. I'm not absolutely sure about that. So the problem is that the hydrogen is massively produced if the wire is transforms martensitically, the bare metal comes into the contact, and the hydrogen diffuses into the matrix, which we believe is assisted by moving phase interfaces. So it's like a hydrogen pump, which is here without any hydrogen atmosphere or without any electrolytic charging. You still have generation of hydrogen. And then, to prove that, we actually should find the correspondence between the oxide cracks and matrix cracks. It was very difficult, we tried, but finally we managed. This is the crack. We made the fibbing cut through it, and we looked at different places here and here where only small cracks are, and in the center where is the big crack. The big crack, the small cracks are not here at all. But here and here you will find the oxide cracks, and here you will find the matrix cracks, and there is a very good correspondence between them. So it's this kind of, for me, confirms the fact that actually the damage comes from the oxide. Well, I will skip this because I'm coming close. This is just more detail about how the cracks look like, and well, instead of conclusion, you can read here this kind of 8 points which explain the mechanism, how the hydrogen damages the nitinol, and figures are kind of track what I have been talking about. So thank you very much.